Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 223. Find minimum time to finish all jobs. Hit the like button, hit the subscribe button, join my Discord, and let me know what you think about this poem. This poem is really weird. I don't know how to prove this in a good way, to be honest. That's why it took me so long. I would say that if you do know your literature, this is an NP problem, so that means that you can really hope to do this in you know do this in any good way, other than exponential kind of way. And the thing is that you're trying to get exponential in a way such that it runs fast enough for this problem, which for me I didn't. So I don't know how to prove this, to be honest. So I will just go over my solution and we'll give a rough bound of the complexity, and then that's yeah, that's the way that I would do it. So yeah, so basically first, like I said, the first thing I looked at is that k is equal to 12, n is equal to 12, but that still said if you do it in a naive backtracking kind of way, it's going to be 12 to the 12 or even 12 factorial or something like that. Either way is too slow, right? Look at the other bound, it's 10 to the 7, it's going to be too slow, or like you can't do anything, or I was thinking that I can't do anything with dynamic programming, at least based on that as a state, because that's too big, right? So I end up hitting on, though I spent a lot of time trying to convince myself that this is right, on just binary search. And the binary search I have, this one looks pretty straightforward for the binary search portion. The rest of it is not, right? Okay, so we just test, and this happens a lot with respect to getting the minimum of the maximum or something like that, where okay, for each number you go, okay, can we do 11? Well, if you can do 11, then that means that you binary search down. If you cannot, then you binary search up to give you more time, because more time can be better. And this is basically based off the monotonic nature of this function, which is basically saying, okay, because if you think about it, you ask yourself, okay, can 10 be an answer? Yes. Then that means that 11 is an answer, that means 12 is an answer, and so forth, right? Once there's a yes, everything after that has to be true, because you can just use the same answer, right? And conversely, if you have 9 is not good, that means that 8 is not good, and 7 is not good, and 6 is not good, and so forth, right? Because if you can't do it with 9, then you cannot do it with smaller number, because you don't have enough time, right? So that's basically the idea behind the binary search. And that's easy to write. But the hard part is how do you test the can we fit it in all time? And what I did is I ended up using backtracking in a little bit clever kind of way, so that I reduced the complexity a little bit. But to be honest, like I said, I don't know how to prove this quite right. And there's some implementation weirdness here to make sure that you code it quite right. That may be a little bit subtle, but basically, most of this is actually pretty straightforward, though, which is that, okay, we have a target that we have to abide by. We have a list of k workers where the total is we start at 0, and then we go through the jobs one by one, backtracking, right? So yeah, for the first, if we are able to get to the end, then we return true. Otherwise, for each for this job, we want to give it to the kth worker, or like for the X worker, from the first worker, the second worker, the third worker, all the way through, and then just try them literally brute force one by one, right? And just making sure that it confines to this constraint where if you add this job to this worker's workload, it is still less than or equal to target. Because if it goes over, then you cancel it, because then that means it's false, right? So the rest of this follows in a way standard backtracking. I look at it, I go, okay, we add the job to the total. We now look at the next job. If we can finish the next job, we return true. Otherwise, we just return totals. Yeah, or like we take this job away from X, and then we give it to another person. So the reason why I have some weirdness here is so that it just makes this. It's a small optimization to make this faster. Basically, what this does, the key part is this part. And basically, what this part does is that if total is equal to, say, even in the very beginning, right? If you have 0, 0, 0, 0, 0, 0, 0, 0, what happens? What I'm doing here is that let's say I have jobs sub 0 is equal to, I don't know, it doesn't matter, right? Like 6 or 8 because it's a lucky number, right? So if you naively write this, which I actually got it wrong, or I got a TLE from this, this would be this, and then, you know. And then you would also try, you know, this and so forth, right? And this is obviously going to be, you know, these answers are, you know, you're doing a lot of permutations of the inputs, which doesn't really help. So yeah. So that's basically what this does, is that if we try, you know, if this index is equal to this index, then we just don't try to put it in here, right? Because we know that it's going to give us the same answer, whether it is true or not. So that's basically what I did. To be honest, during the contest and now even, I am not able to prove that this is good enough. It's just that when I submitted during the contest, there was a case where it was too slow. This case, actually, because I think it's going to be end up like 10 factorial almost, which is way too slow. So if I added this at least makes this much faster, because it removes a lot of the possible permutation of just basically the same thing, right? So yeah, but I wasn't sure that this was enough, and I thought that I might need to add more filtering or something like that. And to be honest, knowing that this problem is NP plus, NP, either NP or NP complete during the contest, I knew that I had to do something here, even though I took a long time to really convince myself that there was no alternate way of doing it. Because then once you realize it's NP, then you can only figure out how to optimize this. And I think this is why, like, during the contest, a lot of people, like a lot of good people, have a lot of wrong answers, or not wrong answers, but like incorrect submits, which is, I assume, is time limited exceeded. Yeah, I was a little bit slow on this one though. So anyway, you can watch me solve it live next. I would say though, because like most of it was me thinking about it, and like, so a lot of the problem, or a lot of this problem was just like I didn't write that much code, so you should like watch it on 2x or fast forward or whatever. But yeah, in terms of complexity, like I said, this is at, you know, in the worst case going to be n to the k, but there are a lot of cell pruning ways. So yeah, and this is actually I don't know. This is actually very complex. So let's just call it exponential. Is this complexity? And in terms of space, it's going to be linear in the size of k for each person, because and the stack space. So if you want to call it n times k or something like that, that's probably the space, because we only do this recursion, n times, so it's not a big deal. But yeah, let me know what you think. Let me know if you got this during the contest. It took me a while, but yeah, no, I mean, I don't know how I feel about this, but this problem, and there's 2 tracking problems today, so I don't know. Anyway, I will see y'all later, and watch me solve it live during the contest next. Well, people are really fast. 12 jobs. 12 to the 12 is way too slow. Let's see. Do I do max flow? Well, a lot of people got it already. I don't know this one though. I don't have a max flow ready. Yeah, a lot of people got it, but I don't know this one. Oh, clearly. Pretty sure this is NP though, so that's why I don't know. Am I wrong? It's 12 choose 6. It's 12 factor. Okay, let's see. 12 factor is too big. Well, I should know this one, but I mean, I'm thinking about binary research. I'm thinking about a lot of stuff, but the sum of k numbers. Yeah, let's try it. One try this one. Okay. Oh, that actually went. Time limited. Yeah, okay. I knew it was. I don't know what the answer is then. Why is this time limited though? Well, this is just doing 10 factorial stuff, so that's a little bit dumb. Definitely save some time if. This is okay. So what do we want to do? We want. How do we want to do it? Basically, this is doing like 10 factorial stuff. How come this didn't catch it? Oh, maybe I just needed one more number. Not sure what's special about this case. But okay, that was just me being a little. Hey everybody, yeah, thanks for watching. Let me know what you think about this problem and other problems on this contest. And I mean, it's been a while since I finished in the top 100, so I don't know. I will talk to you later. Bye bye. Oops, one button.